All right, hello everybody. My name is Michelle at Google, and I'm going to begin with an update on the volume, topology, and local versus volume work I've been working on the last few releases. And also after, well, I guess we'll hear. First, I'm going to talk about what we have done so far up to 110. Then I'm going to go into some of the design elements and features that we're adding for 111. Then also talk about our roadmap beyond that, and then open it up for discussions on some future design elements that we're looking at currently. So to recap, basically, move both the volume scheduling and local volume features to data. So what that means, I'll cover the topology part first. We've added a new generic topology mechanism into persistent volumes. So now you can specify a node affinity on persistent volume, and this allows the scheduler to be able to schedule the pods that are using those volumes to appropriate nodes where the volumes can be accessible from. So today this is most applicable to local persistent volumes, but also applicable to solo volumes such as GCEPD and AWS. And tomorrow this can be used to support some of the more advanced distributed storage systems that might keep replicas across systems. So the other important aspect of this feature is that we need to integrate scheduling and make it more tightly coupled to volume binding. So previously what happened was that when you create your PVC, the volume controller immediately starts to try to bind or dynamically provision volumes for it. But because of that, it can't actually look at any of the mod requirements. So it might actually bind to volumes that were on nodes that couldn't actually run your pods. So we've added this new volume binding mode to delay PVC binding until a pod is actually scheduled that uses that PVC. And then as part of that, we've migrated a portion of the volume binding logic into the scheduler. So it handles two cases. First, if your PVC is already down to a TD, that's the easy case. All you have to do is look at the node affinity on the persistent volume and evaluate it against the labels on the node to see if you can schedule that pod to that node. The harder case is if the PVC is not bound. In those cases, you either need to try to bind it to an existing persistent volume, or you have to trigger dynamic provisioning. So in 110, we've implemented support for the first part to choose to bind to a pre-created persistent volume. So what this will do is now the scheduler is going to loop through all the persistent volumes in the system, find one that satisfies the current node, and then it will handle the binding of the PVC to the TD. The other major use case that this enables is that if you specify multiple PVCs in a pod, we will actually choose local volumes all on the same node so that your pod can actually run. So that's on the general volume topology side. So if you go back, all of this logic is in the persistent volume object, and it's not tied to any specific volume type. So you can actually use these features in any volume plugin today. So now going to the local persistent volume side, what we've done is we've added a new volume plugin to handle local volumes. One big difference, so this is meant to be an improved host path essentially, and the major difference here is that you can only use a local volume that's volume. By doing this, we can avoid a lot of the issues of using host path volumes directly in mind in the pod. Right now, the local volume source only supports directories and mount points, and block devices. Block device support is outside. So in the beta, support is supports directories and mount points. One limitation is that you must already have the directory or mount point formatted and globally mounted somewhere on your node. But that is something we are looking at improving in the future. One more part of the feature is an external static provisioner, which is an optional that we want to be able to use OPVs in large clusters. One important thing to note is that this is not a provisioner. This is what we call a static provisioner, in that we will look at all of the, we will basically, when you set up your mount points on the nodes, you will mount them into some specific directories that this provisioner understands. And when we detect new mount points in those directories, we will pre-create the persistent volumes for them. And then when the pod consumes them and then releases the PVCs, then we will also handle cleanup of those local disks and also reactive tagging. So this runs as a daemon set on every node. And you guys, when you have time, you guys should check out the QCon talk that Ian and I gave on this topic. We basically went into a deep dive on this external static provisioner and gave and demoed some examples of how it's actually used in a real production environment. So I would highly recommend checking out that demo. So going forward into 1.11, what's next? So in 1.10, we added support to delay binding post-statically created PDs. So now the next logical step is to enable support for dynamic provisioning scheduler. And basically, we need to consider, when we are considering what nodes or zones or topologies would be most appropriate to provision the storage in, we have to take inputs from 3 different places. First, we have to take inputs from the pod. We have to consider all the resource requests, any affinities, or selectors they might have, pod affinity, and consolidation. All of those aspects that influence pod scheduling, we also need to will get considered as part of running in scheduler. The second part that can influence the dynamic provisioning decision are any restrictions made by the administrator. So the administrator might just have some policies to reduce the zones that a volume can be provisioned in. Today we have these topology restrictions as opaque parameters in the storage class. So for plugins like JCDPD, there's like a opaque parameter called zones that you can restrict the zones that the volume can be provisioned in. Where basically here we want to make that topology a first class field in the source class. That way we can actually incorporate it into the scheduler without having to add plugin topology to the scheduler.
So which one of these mechanisms lets me ensure that 2 PVs end up on the same node, but I don't care which node?
It's basically it's not any of these. So actually, you don't have to specify any of this. It is the scheduler code that will process the PVCs in one go. So it will evaluate if you have multiple PVCs in your pod, the scheduler code is going to make the provisioning or the binding decision by first making sure that all the PVCs and the decisions, the possible volume choices that it makes for each PVC is all consistent with each other.
Okay.
So I guess to kind of give an example, previously the PV controller would just process one PVC at a time. And then given one PVC, it would find a volume to bind to, then bind it. And then move on to the second PVC, and then find a volume to bind to and bind it. But the PV controller has no way to correlate that two PVCs might be related to each other, like they might be referenced by the same pod, and therefore both the PVs need to be runnable on the same node. That was the old way in the PV controller, but now that we have this logic in the scheduler, and the scheduler operates at the pod level and not PVC level, we're able to basically make the volume binding decisions. We're able to correlate the fact that multiple PVCs might be related to each other by a pod.
So it's actually the two PVCs to the same pod.
Yeah.
Is the same for people?
Yeah. As no, this is a thermal plugin to the scheduler. As in, the scheduler has
Like a list of plugins.
yeah, there's like the scheduler has predicates and priorities, and you can either have the code in tree and built into default scheduler, or you can build it out of tree with the scheduler extender, and then you configure your the default scheduler to call out to your extender.
Okay, so that's both.
Yeah. So this logic is built in tree in the default scheduler to because basically we're operating on cores within these objects, and it would be a pain for deployment if any point that you have to add a new extender for a core object.
I was curious if you could override it mostly.
No, you can't override it. Well, okay. You can configure your default scheduler. You can configure which predicates run your default scheduler. So it's like this is lucky.
Shut it off and put your own predicates in.
And then the third input that we need to take into account is from the storage provider itself. Here, we're mainly looking at potential capacity limitations on the underlying storage. So as an example, to support local volume provisioning, we are looking at implementing a OEM-based provisioner, and every volume group on each node is going to have some capacity limits. So we need some sort of way for the dynamic provisioners for the local LVMs to be able to be capacity they have available, and so that the scheduler can take that into account when choosing the node for the pod.
One of the goals is to write an LPM.
Yeah.
And who's going to write that?
Oh, the community.
Yeah. So what I mean by that is it can LPM can be a little bit complicated to write a provisioner for, because you have to be careful on how many debuggers support snapshots in it.
At the first phase, probably not.
If you will, anyway, what I'm going to say is that you have to be careful on how you interface with it, the amount of metadata you provide for it, because it's very static thing. Just be careful.
Yeah. have, yeah, so basically going forward, the initial volume plugin support that we plan to do for this is first the zonal volumes, GC, CDS, CDS. Second, there's another effort going on to write an external provisioner using LVM. There's a separate design document for that. So if you have inputs, feel free to go there to read it. Yeah, check it. Yeah, so please take a look at that. I know LVM is pretty heavy, so yeah, all the things. Yeah.
The slides and the slides with the company, are they attached to the document?
They will be. And then the third part is we're going to be working on introducing topology ordinance into the CSI stack so that eventually, any CSI driver can take advantage of this. And then on the local volume side, we plan to make additional improvements into the plugin itself. So one thing I mentioned at the beginning was that right now you need to pre-format and mount the file systems that you want to expose. We're looking at doing that work in the plugin instead. So in the new model, what will happen is you can just pass in the block device, and then if the PDC is a file system type, then we will actually handle formatting and mounting. And this is more in line with how other volume plugins today handle things. They implicitly support this file on block mode. And actually, as an open issue, I would like, for this reason and for the other reasons of secure runtimes and based runtimes, I would like to explore an explicit file on block support. So we don't have to talk about that here.
File on block support?
Yeah, explicit. Right now it's implicit.
Can you explain it a little more?
Yeah, so right now, if your PVC is a type file, it can only bind to a PV as a type file. And a PVC block can only bind to a file type block. What I would like to allow is, if plugins can support it, allow a PVC as a type file to bind to a PV type block.
Put a file system on it.
Yeah, and then we can explicitly make calls to do file system formatting and mounting.
So just is the purpose just to save the effort of, bringing the file system?
So the two main use cases that I think would benefit from this, one is that it will make the local volume API thinner, because right now in the local volume API we pass it pass. And right now, and a path could be nice, or a path could be directory, or an outpoint. And we will do 3 different actions depending on what those 2 types of inputs are. So if the path is a directory type or a file system type, we just directly pass it through and file system. When we mount it. But if it's a block type, then we do 2 actions depending on if the PV is file or block. If the PV is file, then we go and format the file system on it. If the PV is block, then we pass through. But that in the case of local volumes, because you have to pre-create the PVs first, that means when you pre-create the PVs, you have to decide up front whether your block device is going to be a file system type or block type.
So the use case is it gives you more freedom to not put a file system on it. It's greater.
Yeah, you can create all the local PVs as block, and then if the pod wants to use that file system, then we do the mounting and formatting on it. That was one use case for supporting explicitly supporting file unlock. The other use case was if we want to support better support secure runtime hypervisor-based or VIA-based. For performance reasons, we've seen requests where they want us to directly tap in the block device, and then they do the file system formatting and mounting the hypervisor layer itself. So if we have like an explicit split on the interfaces, that could get better.
But a lot of use cases for the block storage is non-standard file systems like XFS or special database.
Yeah.
That's pluggable. I mean, would you be able to plug in like some kind of XFS like container command?
I'm not sure. I at least would think, well, for our volume layer, we only support the standard. Yeah, for like topics with topic semantics. So
Nobody ever want to put XFS in there.
that's all anything Microsoft has, but yeah.
One more question on the graphic stuff. Is it possible to provide your own drivers to have to provide further implementation of that interface?
Yeah, totally. So like I said earlier,
Through CSI?
yeah. So this design here for supporting dynamic provisioning in the scheduler, it's generic to all volume types, as long as you use the PVC TV interface. So it's going to be supported in the CSI stack. So if you implement CSI volume, you'll be able to return, or you'll get on the create volume request, you'll get passed in certain topology information, and when you create the volume, you can pass back topology information as well. And it's going to leverage all the existing node affinity, the persistent volume node affinity that we add.
The dynamic provisioning that will also require like a volume representation that's stable, right?
The create volume interface and the provision interface will need certain new arguments. Yeah. So I can actually go into this spec. Oh yeah, this one is all queue calling too. Is this too small?
Yes.
Okay. So I'm going to go through a few examples. This is the very basic example where it just basically works out of the box, and we don't have to. The user doesn't really notice anything different. The main, I've used this example in the GCEPD today and how we can take advantage of this topology or dynamic provisioning. Basically, you set up your binding mode in the storage class to be delayed and wait until the first pod comes around. So once you set up the storage class, then as a user, you're going to create a persistent volume claim, specifying your storage class name, and this is exactly the same persistent volume claim that you would use today. The only difference here is now we're not going to immediately bind or trigger provisioning of a volume when you create a PVC. It's going to wait until you create a pod. So now the user creates a pod that uses PVC, and once that happens, now we can run through the scheduler, and the scheduler is going to go and pick a node that can satisfy all the pod's resource requirements and affinity policies, and also make sure that you can provision a volume on that chosen node too. So once the scheduler picks a node, then that node is going to get plugged into the provisioner, and the provisioner will take that node, pull off the topology it needs. In this case, the GCE PD wants zone information, wants to know what zone this node is in. So then it's going to go and provision a GCE PD disk that is in the appropriate zone that has enough resources to run on. And you can see here when after provisioning, now we have this node affinity on the persistent volume that says this volume can only be accessed from nodes that have this zone label set to this particular zone.
This will require cloud provider access.
No, it doesn't.
How the provision then is
Oh, so the GCE PD provisioner needs the cloud provider to provision volume, which already needs today.
Yeah, but the scheduler is a separate process. It doesn't have the.
Yeah, so the scheduler doesn't need to invoke the GCE PD provisioner.
The provisioning still happens in the PDC controller. The scheduler just sets it up to allow the provision to happen.
Yeah, the scheduler just picks the node and passes it to the provisioner, but it doesn't actually call up kind of information to it. So the availability of that.
So you pull again and then pull keyboard actually.
So that's a simple case where there are basically the user has like no inputs and the admin has no inputs, and you just let the scheduler take whatever it takes to do that thing. So now here's a more complicated case where your administrator actually wants to restrict the topology to specific zones. So what we're going to add here is a new allowed topology field in storage class. And this is also going to follow the selector format that already exists today, like the node affinity selectors. And now what the scheduler can do is take a look at the selector that you set in the storage class, and then apply it to the current node that it's evaluating. So we'll just see some examples here. Let's see. I have my basic Zoll example here. I want to restrict that as an administrator. I want to restrict provisioning of this volume to one of these two zones, US Central 1A or 1B. So now in my storage class, I add this new allowed topology field where I specify this provisioning should be restricted to zones US Central 1A and US Central 1B. Let's see. Okay, here's a really complicated example. Let's say I have some cool storage system that does rack-based provisioning. And let's say for whatever reason, I decided I didn't want to make my rack names unique across the whole cluster. So I need two topology keys to uniquely identify the rack. Here I'm using both the zone topology key and the rack topology key to uniquely identify the rack. So to allow this, and so say if as an administrator you want to restrict provisioning to 3 racks, then this is one way you could end up expressing these restrictions here. I don't actually know of any storage systems today that does this. I think most storage systems today can be uniquely identified by a single topology key, but we just wanted to cover all bases here and say this is important. Okay. So going back to the 111 plan that we have here, we do have a lot of risks for being able to deliver this in 111. We still have some API elements under design discussion, and there's a lot of there's a big chain of dependencies for a lot of this work. We can't start the next items until the items are finished. So I think, and with code freeze less than 2 weeks away, I think realistically we'll only be able to partially get some changes in, but it won't really be usable and testable by non-developers until the 112 timeframe. So I guess after this, I guess this will take us into 112 and probably going to beta 115 and beyond. After that, then we can, there's even more things that we can start looking at down the line. The first item is to add better security to global static provisioning. Right now, one big problem is that it runs on the daemon set and it has permissions to create and delete all PVCs or all PVs and modify all PVCs, including ones that are not on nodes that it manages. So what we really like to do is to say for each daemon set instance, restrict its permissions to PVCs, to local PVCs and PVs that are already on its node that it's managing. This requires some new features that SIG Ops is working on to be able to give pod identity to, so that we can figure out what nodes each pod request is coming from. Another new area that we're looking at is to add preferences to topology. So we modeled this persistent volume unit affinity against the pod node affinity, which supports both requirements and preferences. So requirement means that the workload must be scheduled in the same topology where the volume is. Preferences means that it doesn't have to be scheduled in the same topology, but you prefer to maybe for performance reasons. So this is preferences, I think, is more useful for a lot of distributed storage systems that are globally accessible across the cluster, but they might keep their replicas or shards on certain nodes, and you might want to prefer workloads to be scheduled on those nodes for better performance. And then after that, we can also start looking into some health monitoring aspects to be able to monitor problems with the local disks and report them to the persistent volume object and potentially look into possible policies and controllers for handling various errors. So those are all sort of future roadmap items. Let's see. Yeah, so if you're interested in trying out the feature, we have our documentation available here. If you're interested in helping out, I think there are quite a few task items, tasks to do. Although a lot of them have this linear dependency chain, so it might be kind of difficult to handle. But please reach out to me if you're interested in any of these items. And to just point out, we have had an amazing amount of people contribute to both of the topology and local volume projects across various states. There's definitely a lot of work that still needs to be done, so there's always room for more. All right, so that's just the update part that I have on the features. I guess how much time do we have?
40 minutes.
40 minutes. Oh, okay, plenty of time. So I want to dive into some of the controversial aspects of the dynamic provisioning proposal that we're currently still trying to iron out. And it's mainly around how can we report capacity of volumes and be able to support any arbitrary topology that all these plugins may need. So the initial use case we have right now is for our LVM provisioner implementation. So here it's simplified. We have basically an LVM provisioner on every single node, and each node will have some limited capacity. But the main challenge is how do we extend this API to also work for volume types that are not node-based? So if you have a rack-based volume or you have a zone-based volume, how can we represent the capacity that's available there? So the first solution that we started going with was first let's record the capacity in node status. The main problem there is that this only works for local volumes. It doesn't work. It doesn't work if your volume plugin is a rack-based plugin or zone-based plugin, and we're trying to support arbitrary topologies of any storage system. Another issue in general is that the way capacity is recorded in the rest of Kubernetes, so for CPU and memory, assumes that you can basically provision contiguously from the capacity that's available. So if it can't, the current capacity API cannot handle storage systems that might be prone to fragmentation issues. So if you can't continuously provision the volume from the capacity you request or you provide, I guess if you have, so if you say you have like 5 disks of 10 gigs, and you aren't able to provision a volume across multiple disks, you can't report capacity of 50 gigs, even though you have 50 gigs available. So I guess that's the main problem there. Oops. So the second approach that we came up with was to report the capacity per topology value in the storage class object through a map. So how this works is that you have to specify what topology key you're using. So in the local volume case, the topology key is hosting, and then you would take the values, all the possible values of hostname, and stuff it into a map, and have the capacity for each node there. So this putting the capacity in the storage class has a problem in that we can't handle storage systems that share a common storage pool across multiple storage classes because we would end up double counting or undercounting the capacity. So this fragmentation problem. And then the other thing is from the API perspective, there's a lot of backlash against trying to stuff all the possible values into a map. They'd rather have all each value in its own, each topology value in its own independent object.
So instead of asking for the capacity, couldn't you let the provisioner provision the PV? All the provisioners provision PV so you can fulfill it.
Yeah.
And whatever it binds to, let it bind to that one, and the other ones.
Okay. Okay. So one thing is every time someone creates a PV, all the provisioners will provision something for it, and then we can fall back to the logic where we choose an appropriate PV that matches. The main thing is there is to handle scalability. So if say you had 1,000 nodes, and then you had 1,000 nodes to provision a PV for every PVC, you need to, and then eventually we'll choose one of them, but you need to clean up all the rest.
Or you can still just provision one and let it bind on the node. I guess the provisioner one doesn't CD with memory resources. That's what it is.
Yeah, so like.
I guess they could take it as parameter.
Yeah, so the scheduler needs a way to be able to like make a good decision about which node would be the right one to provision in, because if say you have 10 nodes and 9 of them have 1 gig available, and
If the provision though, not even having the scheduler?
Oh, maybe. So if so in the case where you have nine nodes that only have 1 gig left, and the 10th node that has enough space, that 10th node can go ahead and provision, and the PV controller or the scheduler will try to find to it. I guess the main thing is if you have multiple nodes that can satisfy the PVC,
Then it'd be a race.
then which one?
Be a race of provision like we do now. That would actually get some of this code out of the scheduler too. I mean, it's
Like,
the provision.
yeah, the main thing is that there is like how you clean up afterwards. Like if you have 1,000 nodes all provisioned volume, how do they know that they were not the ones that got picked? And then
We'd have to time out after like every minute.
yeah. So that's, I mean, that's possible as like,
Or see that the PVC was found and then clean up their PVs that it wasn't done.
yeah, that's possible as a potential workaround when there's something available. I mean, workaround when like we don't have this solution here. I think it's just like the whole.
Isn't that the least touch solution now?
Yeah, it is the least touch, but I just think there will be a lot of churn. There will be a lot of churn creating all volumes and deleting them over and over again across a number of nodes.
Yeah, I think that's going to be pretty inefficient, and those 999 volumes are sitting around, that capacity can't be used for something else.
You can check it out like we do currently. The first provisioner to write for the PVC to have an important provision is to be the one that provisions it.
Oh, I see. So when you provision, you set the claim rep. Yeah, I think the problem there is no breakout sort of those.
What if it takes the issue out of the scheduler then, doesn't it? I mean,
No, but then you'll end up where you were before, where you could provision a volume on a node that can't go to the pod.
well, that's what I'm saying. The provisioner would have to know about the other resource needed by the.
Yeah.
You have to track that all with the PVC somehow.
Yeah. So right now we put that logic into the scheduler, and the scheduler code assumes that it's the one that's going to set the context on the system volume underneath the decision.
Fine, try to modify your 10 objects.
Yeah, I know.
So what about something where you have like an extra, I guess you would have an extra back and forth with the provisioner, but where it could provide an ordered list of a preference list, if you will. And so then the scheduler could simply go down the list and find the first one that it could actually work with, right? And so now you've got the case where, you know, I've got a node that has a lot of excess capacity. The provisioner would know that and could set that high on the list and put the ones that are more space.
Where's the risk making that?
So you're saying like the new.
It would be an extra back and forth provisioner.
Or like a new object or something that ranks provisioners, or.
Yeah, like some sort of a score somehow.
Does each local provisioner have its own storage class?
No. So the same storage class is used across all nodes. Right now, it doesn't support that. We're trying to make it support that.
So the first solution, the fragmentation problem, right? Can you preempt for I saw a comment that preempting for us not be efficient. The first solution only works for local volumes, assume everything not fragmentation problem.
Yeah, so this is like, so LVM doesn't have a fragmentation issue because it can stitch together the multiple blocks on a continuous volume. But as an example, if you wanted to implement a local volume provisioner based off of rate 0 and partitioning, then you would end up in a fragmentation. You could end up with fragmentation issues. So you could you'll start off with a complete contiguous rate 0 volume, but then you'll provision one that's 100 gigs, one that's 10 gigs, and one that's 100 gigs. And then if you delete the 10 gig one, you end up with a chunk in the middle you can't use.
So instead of reporting total free capacity, perhaps we could report largest volume that can currently be provisioned.
Where you can just return the list, you can install your chunks that are available. This could be a long list.
Yeah.
It's a list.
Okay. Yeah, that's a possibility. In the capacity, instead of being a single value, you can return an array.
Largest is the only one you care about, that way. I mean, if you have a 50 gig partition available, you can always partition 1 gig from it.
Yeah. But so the way that the scheduler works right now is that it doesn't make any callouts to anything. Everything gets cached into the scheduler from API objects. So we need some way to be able to represent stuff in the API object to be cached. And then the scheduler actually it has this thing called a zoom, where it marks the cache as if it had done the provisioning. It does this for performance reasons, so that it can basically do API updates asynchronously in the background, but still be able to process more pods and not have to wait for API updates. So I think it would probably. So one of the main challenges with capacity is that we end up having to do capacity accounting in the scheduler as well. It actually does this today, it should be great. But it's easy because it's contiguous. With something non-contiguous, you might have to pull it out of the smallest chunk. Yeah.
You look at this today for normal
We don't. We don't do capacity reporting.
So why do you?
So this is important. This is important if your volume plugin is limited by its topology. So for things like NFS or cluster that you can access anywhere in the cluster, this doesn't matter. It's important for things like local volumes, so that you can schedule a pod on the node that can run the pod and also have enough capacity to provision a volume on that node. Does that, so say your node A has 10 gigs of space available, and has, say node A has 100 gigs of space available, you create a PVC, we might choose to provision a volume on that node, but that node might not have enough CPUs to run the pod.
So would you do just a lazy try? Find out first if it has a CPU or not. Try and see if it.
Well, so it's going to augment the PVC with your CPU in there, and let the provision.
Well, it's not just CPU that way. There's a long stuff. It's like all of it. It's CPU and memory requests, node affinity and selectors, pod affinity and tag affinity. Any new feature or annotation that the scheduler adds in the future.
Your provisioner have to have all the schedule.
Yeah.
Make its own
And instead of recopying all the scheduler logic you went into our volume provisioner, what we want to do is bring the volume provisioner into the scheduler so that it can handle, we don't have to duplicate all the scheduler logic.
So I think you're going to run into more than just the fragmentation issue that you've already run across, right? In that capacity in your storage system is not something that is, I'm not really sure how to put it, additive, if you will, because I could have a duplication or compression layer under there.
Yeah.
That means that my free capacity is something that is.
Yeah, so So basically the free capacity needs to be reported as from the user's perspective.
But I can give you a number right now for the worst case, but, you know, it's something that's going to change.
Yeah, so this makes a lot of assumptions that one, that your storage system is only used by Kubernetes, because Kubernetes is the one making the resource, doing the resource accounting. And this is actually how other resources are managed in Kubernetes, like CPU and memory. We assume that Kubernetes manages all of it. There's nothing else running on the pod or nothing else running on those nodes outside of Kubernetes.
Sure, that's fine, but I can have two PDs that land together that can dedupe against each other. And so I can actually have extra capacity that's still valid for additional.
I think you're having like a separation of concerns there. Like, there's one that's managing storage, it's not a Kubernetes team. Then you go to a cloud, a public cloud, and you go consume from them. Do they ever show you the efficiency of what they're doing in the back end to save space for you? Yeah, I mean, they charge you as a consumer, and the consumer doesn't get the benefits of the back end efficiency changes. So I think Kubernetes is being consistent with what a public cloud would be advertising to their consumers, no matter what happens in the back end after you give data.
I guess as a storage provider, are you suggesting that I actually tell the user infinite?
I think you got a good point here. Like the challenge is that the way that you count the use of storage is going to vary from storage system, and even within a given storage system, depending on parameters like whether you've got replication on mutation, on the actual capacity that you consume is going to be possibly wrong. So what Kubernetes thinks you use. Not capacity usage.
You could potentially do things like under-reporting.
Right.
You can under-report and then adjust as needed.
So as somebody that's not heard this for like years of debate and arguing, because we have this exact same problem and comes up over and over again. What I finally did, and what I think the right answer is, as a provider, pick what you want to report. In my case, I report the virtual capacity. So all the dedupe stuff and everything else, I'm just taking care of. I'm not telling the user what I'm doing. There's a number that I set up, and from a user's perspective, things are consistent and they just work out. I don't try and be all things to all people because it's never, you're never going to win. If you need to do that, I think you need a separate admin API for a storage admin. But I think what you're saying, especially what you said, or maybe it was Clinton, is from a user perspective, you don't want the user to know what you're doing as far as deep compression and everything, at least in most cases. So,
actually, we we're actually also addressing one at the scheduler level. So they're actually, if it's the same provisioning, then we are looking at different things. Looking at not just we're looking at like oversubscription ratio, looking at the virtually how much you are consuming, really how much we're looking at that. And then if it's not same provisioning, then you just well, we're going to have two co-paths to handle that. And the backend storage will be reporting differently, whether it's both, just one.
I think that's what it boils down to. The deduplication issue I'm not as concerned about because in that case, if you think you're consuming more than you're actually consuming, that's okay. At least you're not going to get into a position where you try to provision and you want that space. It's the replication one that I'm more worried about. Ultimately, if we're going to solve that issue, we need a way to be able to probe the storage system to get the actual usage and have that constantly updated. The problem is that within Kubernetes, nowhere does it do that. Basically, the underlying resources report some capacity, and Kubernetes manages the usage. it's something we can consider in the future. I think the first step is definitely establish a way to report the capacity, have Kubernetes start doing dumb counting with the assumption that it will break with certain systems, and then consider adding in some mechanism to be able to actually probe and get an official real usage. Ultimately, the purpose of this feature is not to be foolproof. Because if the storage system can't provision anything, it's going to fail. It's going to come back to the scheduler. The scheduler will have to pick a new node to provision on. Basically, what this feature is trying to do is optimize and short circuit that. So since it's an optimization, it's not necessarily a solution for everything. We can start off with, okay, let's do our best effort to count correctly, and then in the future, let's try to be smarter about the way that we count. But it doesn't need to be perfect.
I think you're saying the same thing John was saying. You'll never be perfect, right? We're trying to number this pretty close. And yeah, there'll be rare conditions where you'll be wrong. Yeah. Those are exciting.
I agree with the direction, but I sometimes, if I was looking at the storage system, supplies, I'll just put it in
Yeah, that's fine. If yours, this is meant for like when you really have some, you're like you're close to being fully provisioned, and we're actually, failing and retrying across thousands of nodes might actually make sense in performance.
As long as you've got a way to go in and update the counts, right? Like,
yeah.
I mean, if I'm allowed to go in and dynamically change the capacity of my node, I'm okay with that, right? It won't be up to date all the time, but maybe once every 10 minutes I can go and figure out what my current DB ratio is, and how my snapshots are doing, and then update my capacity.
But that's going to be really hard to do because there's going to be a big deal of DBs coming down. Sure. And so it's like, these are the ones I know this is nothing. This is so random. Right? It's so random. Take a point. Now I'm sorry.
Yeah, and keep in mind, this is really mostly beneficial for storage systems that have topology restrictions, like local storage and zone storage or rack-based storage. If you have like a distributed system that is available globally, this capacity thing is not useful for you.
I think this is only what I'm doing. That's the way I kind of do it. Just don't see the getting out.
Well, we're interested in policy performance for this, so we can do stuff like co-locating.
Yeah. So for
it's not going to be local.
Yeah. So for like performance reasons, what I mentioned earlier, I think topology preferences will be the most useful thing. So this is basically in the persistent. So when you provision, you can create your persistent volume with node affinity, and in the node affinity, you can have a preference field saying, I prefer that you schedule your workloads to these nodes. But it doesn't have to be a requirement. I think the capacity proposal that we're aiming at here is mostly for the requirement part of provisioning, as in like the workload won't actually be able to run if you don't provision it in the right place.
So I'm thinking backwards, like, do we need to do that provisioning for local storage at all? Sounds like it's like it's a difficult problem.
I think I personally don't feel like local volume provisioning is the right direction to go in, but I think especially in bare metal environments, there seems to be a lot of value.
Yeah.
But on the cloud provider front, I think for cloud provider environments, you really want to utilize the maximum performance of local disks. not so much, higher disk utilization.
That's it, but like as long as like there's another people that we cannot get comfortable with, you write this survey and keys and GPs and all this stuff for the local devices that unrelated but kind of related.
Yeah.
We solve that problem.
So like the static local PV is useful for those where you want to like use a full disk. But I think there's some like one-off use cases where you might want to share disks and carve out smaller volumes of them. But for like the really high performance use cases, you just use individual disks, I agree. Yeah. So this effort, I think this effort is being largely driven by a lot of other community members to support this LVM part. This is what we really want.
Can this work without API server running? So in instances where you may want to bootstrap your node or partition disks to be used as a local storage provision.
No, it depends on Kubernetes API objects. Okay.
I think my main concern is like in particular with how the local capacity is used and difficult to solve at this stage.
It is. So I think at least with the LVM implementation, you can get rid of the fragmentation level.
But LVM is like, for example, we're using like something like Kubernetes and that also serve volumes. So you might have more users or like some other
I can't hear what you're saying.
So I'm saying that like if you're using something like Kubernetes versus CFS, then you might not want to use that. And just want to use the sub-volume to serve your stuff.
Yeah, so I think the most important. Yeah, I think the most important thing is like we can build. We don't want to build any APIs in Kubernetes that are volume plugin specific. If we can come up with some APIs that work across all volume types, then people can implement whatever types of provisioners that they want. So I think that's the main challenge. But I think there's some good takeaways from this discussion, and I think I would really, let's see. I think it'd be great if like you, John and Shane from the staff side can contribute some more comments on the PR and stuff discussion. That'd be great.
Yeah, how do you have for like 50 people, but 3 people are going to comment on PRs? We need more comments.
It's okay. I comment on my own first. Okay, so I think that's all I wanted to discuss here. Does anyone have any other questions about anything? Life?
What can we do it in not now, but as we go forward? So with looks like we have the LVM one. Hey, bud.
Cool.
It's hey, we have the issue with LVM.
Yeah. Oh yeah. So that's like a downside of dynamic provisioning of local volumes. You totally have the OC neighbor problem. Yeah, that's a trade-off. That's the main reason why I don't think people should use LVM based dynamic provisioning, but some people still want to. Yeah, if you have any other wisdom on LVM, go ahead and comment on that. LVM proposal. Yeah.
Ask a question about this. Why is the notion other stores? Why is it against this?
So this is basically so with local volumes today, without dynamic provisioning, what happens is you can expose each disk as a volume, so you don't have noise in the multiplier. But now that we're introducing dynamic provisioning, we can carve out volumes from one shared disk.
Makes sense. The question is whether it could be made a Kubernetes wide feature as some sort of QoS controls and volumes.
That's another remarks.
That's what I meant by feature.
So I think this topic has come up a lot. Like I think people have asked to have like C group support for the IO disk IO scheduler, and there's a giant debate.
I think so. Yeah, anybody can do it on their own. Right? They can have their own source classes, they have their own attributes, and do whatever they want.
The storage system can do it. Yes, with LVM delay, we're just going raw to this, that's the hard part.
Yeah, that's a lot harder, and especially mentioned across a homogeneous group of storage devices. I'm not sure. I mean, it'd be interesting to consider and talk about, but we could probably fight about that.
It's a research project right there.
Huh?
I think it's a research project.
Yeah.
Yeah, we tried for I think years to implement an IO-based scheduler in org, and gave me work.
I can so.
Yeah.
It so happens.
But you can talk to like Michael Rubin, he has a lot of background on all the reasons why the disk type of scheduler didn't work on scale. So.
Should it be at the node level, or should we have it in a cluster scope against this?
Yeah, so the main challenge here is that right now the only way Kubernetes to report capacity is on the node level, but that would only make things work for local volumes. And it wouldn't be able to support other volume types that is only used for that disk or any other arbitrary topology base. So one of the things we're trying to look at here in this proposal is how we can represent the capacity in a and support arbitrary topologies at the same time. So like we don't want all volumes to report capacity in node. Makes sense for any. Anything else?
Chris, do you have a question?
Yeah, I have a question. So if local volume is meant to be host path, you want to block host path by the data exception services for a while. Is there, and maybe I'm just blind this time, is there a method today to create a local PV on all nodes, and then have it be the same name on all nodes? And so to an end user, to have a host path example is give me volume ball 0 on all those that I ever know. I don't really care where I get scheduled, as long as it has that ball 0 on that node.
Yeah, I think the local PVs weren't designed for that use case. It's more designed for in use with stateful sets where you actually need identity. Like each volume is treated.
So then is there a plan like this, right? So host path like, but giving an option that is just a directory path or volume or whatever, that's just scratch this, we'll give it the same name on any nodes on it.
At that point, why not just do an empty dir?
I think probably empty dir is just like no matter where it's mounted. But it's mapped.
Do you still want data gravity?
Yeah.
I think there was one issue with empty dir because empty dir is based on boot disk. And if your boot disk is too small for scratch.
And empty dir also gets.
Yeah.
I want to, like, let's say, like, this is really important for, like, logics. I want my logic to be written to disk forever, right? And the only time it ever gets removed is if the process is one that removes it. The empty dir doesn't work for that because if the log gets scrubbed, all the logs that are written might be sensitive.
So you could potentially do something like, you could configure the local volume static provisioner to look for and configure the discovery directory to be to include your directory, that's the same across all the nodes. And then you can put labels on the PDs, saying like this PD is intended for a label on it, and all your PVCs use the same label. And they're gonna all bind to only, or you can use labels or you can use storage classes, put them all in their own unique storage class. As long as your PVCs use the same storage class or the same label, they're only gonna get bound to those sets of PVCs. So you might be able to do it that way.
Will there still be a challenge where like deployments now scale
Yeah, so because it uses PVCs, it can only really scale up stable sets. Because you need a unique volume, you need unique PVC per instance. While deployments and daemon sets right now all share the same PVC. But I think it might be possible to extend daemon sets at least to have like a volume claim template like stable sets does. Because you can usually associate an identity to the node on the daemon set, but for something like deployment, there's no such thing as identity, the persistent identity.
Okay, so host path it is.
Yeah, if you still need to use deployments.
We'll get you off of host path one day.
I don't want to use that, it's for a specific fire.
Interesting use case.
Can you use PC for the system?
Well, I don't think, let's say you have 10,000 copies of the file, or 10,000 pieces of the volume. That just seems crazy. Most stores.
It gets you away from
That's true, but it also still requires a deployment issue. I have to be stable sets now. Instead of, anyway, I was just curious. So it would be nice to have like some like mobile PV that consume that to remove the host path. But anyway,
maybe there's a way to take, if you're deploying Kubernetes, it would be nice to put host path on a specific disk. Where, not just anywhere, just I would say host path goes here on this. It's like giving it its own PV on each node, and then they're bound to not go through more than that disk. If you could do that.
or you can make host path maybe specific, so like a path.
Yes.
And you can only get ready for that.
I mean, if you deploy Kubernetes, then you go whatever.
That's true. Okay.
You know, I think actually the original proposal for local volume management, which is 2 years ago or something, Vish actually put in a proposal for logging volumes. That might, that was like a long time ago, and a lot of stuff probably has changed, but could potentially try to revisit that. So if you look at the original design proposal, which was 306, I think, there's some section at the bottom about logging volumes, or the log, specifically for the logging use case. Cool. Thank you.